Hey YouTube, Zach Stone here, lead instructor for Electrical PE Review's online review course for the Electrical Power PE exam. The following video was taken directly from our lesson on rotating machines. If you'd like to try this lesson out for free, along with many others, come check us out at www.electricalpereview.com. Link is in the description of this video. You can sign up for free to try out a variety of lessons. All you need is a valid email address. Alright, that's it. Enjoy the following video lesson on induction motor no load and locked rotor test. It's time for some practice with the induction motor no load and locked rotor test. The problem states 5,300 watts and 50 amps are the measured results of a no load test performed on a three-phase Y-connected motor rated for 575 volts. 48,000 watts and 150 amps were also measured during a locked rotor test performed on the same motor with an applied line voltage of 220 volts. Determine the following values: stator resistance per phase, total no load apparent power, magnetizing reactance, core, winding, and friction resistance, total locked rotor apparent power, total locked rotor reactive power, leakage reactance, and finally the rotor resistance at locked rotor, also known as the slip resistance. The stator resistance of the motor, measured across two terminals, is 1.3 ohms. Alright, before we begin, I just want to say this is not a 6-minute problem, and chances are you will not see a problem of this depth on the PE exam. However, a 6-minute exam problem could be taken from just about every single one of these individual steps and individual values that we're going to be solving for. So that means if you can get comfortable following along each and every one of these steps, and you can understand confidently why and where the values come from, that means you'll do just fine on any no load and lock rotor test. Alright, let's begin. I like to start by showing drawings and working with figures, so let's look at the induction motor equivalent circuit. The problem gave us quite a bit of information to digest, so let's try to organize that in a way that will make working with it easier. So first thing is we know we're dealing with a three-phase induction motor that's rated for 575 volts. We know that this is a line voltage value. Why? Easy, because it's of course a three-phase motor. Next, we're given the results of both a no load and a locked rotor test. The no load results were a measured 5,300 watts of active power and 50 amps of current. The lock rotor test measured 48,000 watts of active power and 150 amps of current when there is an applied line voltage of 220 volts. All right, let's tackle this problem. First question asks us to find, number one, is the stator resistance per phase. So this is a three-phase Y-connected motor. So if we were to visualize this motor as a Y diagram, it would look something like this. The problem says the stator resistance of the motor measured across two terminals, so we'll pick on any two, is 1.3 ohms. Now it's safe to assume the winding resistance is going to be the same in each phase. That means to find the winding resistance of just any one phase can be found by dividing the 1.3 by 2. This results in a stator resistance per phase of 0.65 ohms. And this is the value of R1 shown right here. So R1 for this particular motor is going to be 0.65 ohms. And again, this is just the stator resistance per phase. All right, next question. Number 2 asks to find the total no load apparent power. How do we do that? We know the total no load active power, but we don't know power factor. So that's not going to help us very much. Let's think back to our standard three-phase formula for apparent power that says it's going to equal the square root of 3 times the magnitude of the line voltage times the magnitude of the line current. Now let's look at this. This is a three-phase quantity, as is the total no-load power we're looking for, except this time we're just looking for the no-load value. So this means all we need to do is pick the right voltage and current values and we can solve. So we know the square root of 3 doesn't change. Now, what voltage was applied during the no-load test? It's going to be the rated line voltage of 575 volts. All right, when we did that during the no-load test, what current was measured? Well, we know 50 amps were measured. So all we do then is multiply by 50 amps. When I punch this in my calculator, I get the square root 3 times 575 times 50 amps. I get a total apparent power during the no-load test of 49,796 volt amps, rounding to the nearest volt amp. All right, that's step 2. Now, we're going to leave this on screen for a bit because it's going to help us answer step 3. Step 3 asks for the magnetizing reactance. All right, before we get confused on what that is, we know what a reactance is, right? A reactance is going to be either an inductor or a capacitor. There's no capacitors on the circuit. There's only 2 inductors. There's one here and there's one here. We know that this parallel branch is the magnetizing branch. We know that these are the stator impedance values, and we know that this is the rotor slip resistance. That makes this inductor right here, capital X of M, our magnetizing reactance. Now, how do we solve for the magnetizing reactance? Well, if we knew the power that was being consumed by this inductor, then we could solve for the impedance value. So could we do that? Sure we can, right? We know what? We now know 2 legs of our power triangle for the no-load test. We know our apparent power no-load. We know our active power no-load, given in the problem. So now we can solve for Q no-load. To solve for Q no-load, all we need to use is the Pythagorean theorem. So that's going to state our Q no-load is going to equal to the square root of our S no-load squared minus our P no-load squared. So that's going to look like this. Our reactive no-load power is going to be the square root of 49,796 volt amps squared minus 5,300 watts squared. All under that square root sign. All right, I'm going to grab my calculator and I'm going to punch that in as the square root of 49,796 squared minus 5,300 squared. And I get 49,513 VAR, rounded to the nearest VAR. All right, now what? We know our total reactive power in the magnetizing branch. How do we find the magnetizing reactance? Recall from the Power Fundamentals Bootcamp when we talked about our I squared Z and our V squared over Z equations. For a three-phase system, our apparent power can be found using our line voltage squared divided by our impedance. But instead of apparent power, if we plug in reactive power, then that means this value won't just be the impedance, it will actually be the reactance. So let's go ahead and plug in these values and see what we find. We can say Q no load is going to equal to what voltage is used during the no load test? That's going to be our applied line-to-line rated voltage. So 575 volts squared. Next, the only way that that power is going to be absorbed is if it's being absorbed by our magnetizing reactance, X of M. So we can solve for X of M by manipulating the formula by dividing our line voltage squared by our total reactive power during the no-load test, which was 49,513 VARs. All right, I'm going to plug this in my calculator. I've got 575 squared divided by 49,513. When I hit enter, I get 6.68 ohms. So that's the value of our magnetizing reactance, capital X of M. 6.68 ohms. And it is an inductor. It's a reactive inductor. So we do have the imaginary J component there as well. Okay, next question. Now we're being asked for our core, winding, and friction resistance. We've got 1, 2, 3 resistors. We know that's not it because that is our rotor. We know this isn't it because we already solved for it. Capital R of M represents our core, winding, and friction resistance. So how do we solve for it? Well, just like solving for our magnetizing reactance, if we can find the power that this resistor absorbs, then we can use our I squared Z or V squared over Z equations to solve for just R of M. So how do we do that? Well, let's try to understand what we know so far. We're still dealing with our no-load quantities right here, and we were given our P no-load. Our P no-load is going to be the sum of any power absorbed by only resistive impedances, not inductors. So if this is our total, then we know this total is going to be the sum of the power absorbed in the resistive term we're looking for and the power absorbed in our stator resistance that we already solved for, lowercase r of 1. Okay, let's expand on this formula further. So we can say our total no-load power that we know is going to equal to the power absorbed in our magnetizing resistor, which is what we're looking for, plus we can solve for the power absorbed in that resistor, this one right here, using 3 times our no-load current squared times the resistive value R1. So recognize that all this is just saying that 3-phase power is equal to 3 times the current squared times the resistive value. That's all that is, so don't let that confuse you. All right, let's go ahead and rearrange this. We'll plug in our 5300 watts for a P no load. We'll plug in 0.65 ohms for a little R of 1, and then we'll solve for the power absorbed just in that resistor right here. So we can say that P R of M equals our no-load power, 5,300 watts, minus, here's this side of the formula, 3 times 50 amps squared times 0.65 ohms. I plug that into my calculator, and I've got the same thing, 5,300 minus 3 times 50 squared times 0.65. I have a total of 425 watts. Okay? This means this resistor right here, capital R of M, is absorbing a total of 425 watts. Okay, we're not done yet, because we're actually looking for not the power losses due to the core winding the friction, but we're looking for the actual resistive value. So just like before, we know the applied voltage across that resistor. it's going to be the same from here to here since this branch is in parallel. And we know that voltage is going to be the rated voltage because that's the voltage that's applied during a no-load test. That means we can rewrite this to say the power across our magnetizing resistance is equal to our line voltage squared divided by the resistive value. Remember, this is still a three-phase quantity. Let's go ahead and rewrite this, solving for R of M, and we'll plug in the values. So I get R of M equals 575 volts squared divided by the 425 watts that we just solved for. All right, I'm going to pick up my calculator and punch this in. And I've got 575 volts squared divided by 425 watts. I hit enter, and rounding to the nearest ohm, I get 778 ohms. That means the resistance of this resistor here, which represents the core, winding, and friction resistance, is equal to 778 ohms. What's next? Question 5 asks for the total locked rotor apparent power. Aha, locked rotor. So we're no longer dealing with this information, but we're dealing with this information. Locked rotor pretty much means you prevent the rotor from spinning, hence locked rotor. You apply a voltage typically until you measure the rated amperage, or you just take the ratio of whatever voltage was applied and the measured current at the same time. So, total locked rotor apparent power. Just like we did before, what do we know that could help us solve for this? We know P, locked rotor, but we don't know power factor, so that's no help. However, we do know both what? The current and the voltage, right? The current and the voltage that resulted in the 48,000 watts of active power, and that resulted in the total locked rotor apparent power that we're looking to solve for. So once again, we just use a standard three-phase apparent power formula, which says the magnitude of a three-phase apparent power is going to be equal to the square root of 3 times the magnitude of the line voltage times the magnitude of the line current. And again, in this case, if we want to solve for the apparent power during the locked rotor test, then that means all we have to do is plug in the line voltage during our locked rotor test, which was 220 volts, and we have to plug in the current that was measured during our locked rotor test, which was 150 amps. All right, I'm going to plug this in my calculator, and I've got square root 3 times 220 times 150 amps, and I arrive at 57,158 volt amps rounded to the nearest VA. All right, easy enough. Next question asks for the total locked rotor reactive power, or kVAR. Well, how do we find that? Well, let's take a look. If we visualize a power triangle, and we're only concerned with the locked rotor values this time, well, we were given our P locked rotor. We just solved for our S locked rotor. That means we have enough information to solve for kVAR, or our total locked rotor reactive power. So let's rewrite this. We'll use the Pythagorean theorem, solving for Q, to say Q locked rotor is going to equal the square root of S locked rotor squared minus P locked rotor squared. Filling in the quantities, that means it's going to be the square root of 57,158 volt amps squared minus 48,000 watts, also squared, all under the square root sign. Picking up my calculator, I'm going to punch in the square root of 57,158 squared minus 48,000 squared. Enter. And I come up with 31,033 VA. VAR, rounded to the nearest VAR. Okay, so far so good. That takes care of 6. 7 says the leakage reactance. So again, before we let these terms confuse us, let's break them down. First, reactance. There's 2 reactances right here. We know that this is the magnetizing or core reactance. So we know the leakage reactance by process of elimination must be our lowercase x. And during a locked rotor test, our rotor and stator branch pulls so much current that we can more or less neglect the magnetizing branch. That means since there's only one reactive impedance in this branch right here, which is in fact our leakage reactance, it must be solely responsible for the reactive power in the locked rotor, right? Since any active power in the locked rotor would also only be due to resistive devices only. Okay, that means since we know our reactive locked rotor power, we can already solve for our leakage reactance. However, this time instead of doing the V squared over Z formula, we're going to need to use the I squared Z formula. And why is that? Do we know what the voltage is directly across the device we're solving for? No, we don't, do we? Because each of these 3 impedances are in series, so the voltage will be different. However, do we know the current that's flowing through it? Sure we do. The current flowing through it is precisely what was measured during the locked rotor test. So since we know I locked rotor, we're going to use current squared times impedance. And that's going to look something like this. Our I squared Z formula says, for apparent power, we'll start there and we'll work our way down. Single phase apparent power will equal I squared times Z. Now, are we interested in single phase power or are we interested in 3-phase power? 3-phase power, right? Well, we know we can go from single phase power to 3-phase power by multiplying by 3. So 3-phase power is going to be 3 times I squared Z. Now, this Z represents both reactive components and resistive components. And this S is all of the power, right? Well, we know the power that's just consumed by this element, so that means we can say Q 3-phase equals 3 times I squared X, or really J of X. Now, if any of this is confusing to you, please make sure you do spend some time in the Power Fundamentals Bootcamp. It clears all of this up. Makes it real simple. Okay, so if I go ahead and plug in my locked rotor value for this 3-phase reactive value, that means I'm going to need to plug in my locked rotor current that we already know. And that means I get to solve for my leakage reactance. How about that? So let's go ahead and solve for J of X and plug in the values as we go along. So rewriting this, I have J of X equals 31,033 VAR divided by, from left to right, 3 times I squared locked rotor. That's going to be 3 times 150 amps squared. All right, picking up my calculator, I've got 31,033 divided by 3 times 150 squared results in a leakage reactance of 0. I'm going to round 46 ohms. That means this value right here, our lowercase x, is going to be 0.46 ohms. And just as before, we'll go ahead and get in the good habit of putting that J in front of that reactive impedance. All right, we're getting close. 8. The rotor resistance at locked rotor also known as slip resistance. What does that mean? Well, recall that the formula for slip is going to be the difference between our synchronous speed, our rotor speed, compared to the synchronous speed. At locked rotor, our rotor isn't moving. That means the actual speed of that rotor is 0. Synchronous speed minus 0 divided by synchronous speed will always end up giving us a slip of 1. That means our rotor resistance at locked rotor, or our slip resistance, is just the value of R2 since S equals to 1. So this rotor resistance right here means that the resistance of our rotor, when modeled as a single-phase equivalent circuit, is largely dependent upon slip. It will change as that S value either increases or decreases. So how do we find just R2 since we're dealing with the slip resistance or our rotor resistance during a locked rotor condition? Well, let's look at the quantities given. So we know that three-phase power is equal to 3 times I squared R. Now we want to plug in our locked rotor values. That means this is going to really be our locked rotor power, which is 48,000 watts. And that means our current is really going to be our locked rotor current of 150 amps squared. And this R value here is actually going to represent both the stator resistance and our rotor resistance. Why? Well, recall that this 48,000 watts, that's our total locked rotor power. Meaning that's the active power in watts absorbed from any resistive element in that branch. So we actually need to rewrite this R as the sum of both the stator resistance that we already solved for and R of 2, right? And again, we're neglecting that S value because we're asking to solve when S equals to 1. All right, we're going to plug in for little r of 1, that 0.65 ohm value we found as step 1 of this problem, and then we're going to solve for R2. So to do that, let's rewrite this. Let's rewrite this by dividing the 48,000 watts by 3 times our current squared. That leaves us with just R1 and R2. So let's isolate R2 since that's what we're solving for. So we'll rewrite this as R2 equals the same 48,000 watts divided by 3 times the current squared minus the R1 value, since we're essentially just moving it to the other side of the equation. We said that little R1 value is going to be 0.65 ohms. All right, last step of the problem. I'm going to enter this in my calculator as 48,000 divided by 3 times 150 squared minus 0.65 ohms. And I come up with a rotor resistive value at a slip of 1 to equal 0.061 ohms. One more piece of useful information. If you're asked to solve for the rotor resistance at, say, a slip of 0.7, well, you'd follow the same exact step, right? Since you just solved for R of 2. And then if you know the slip, all you have to do is divide that R2 value by the slip at which you're solving for the rotor resistance at. All right, I hope this wasn't too in-depth for anyone watching. My suggestions are, if any of the power formula parts gave you trouble or made you scratch your head, do me a favor and spend some time in the Power Fundamentals Bootcamp. That will take you all the way from A to Z, starting with single phase values all the way to 3-phase values, looking at the I squared Z equations, the V squared over Z equations, and just about everything else you can think of. So that'll really help you with this problem. Next is to remember that on the actual PE exam, you could be given all of this information here and then only asked to solve for one of these individual answers. That would be a safe consideration for a 6-minute problem. So chances are you're going to need to rework this problem once or twice to finally get the hang of it, but I think you'll feel a lot more confident with induction motor no load and the locked rotor test.